Transformer models use self-attention, which scales quadratically with sequence length, making it computationally expensive for long sequences. Recurrent models use a hidden state, which may not have the ability to model larger sequences, thus reducing long context performance. As such, modern architectures struggle with storing novel long context information that they encounter after training. The Titans paper, introduced by Google in December of 2024, seeks to address this, primarily by incorporating a standard attention mechanism, a set of persistent learned weights, and a novel neural memory module. This module is a dense neural network whose parameters are updated during inference. Across variants of the Titans architecture, the inclusion of a neural memory module resulted in stronger benchmark performance than Transformers or Mamba.
Now, there's a key problem with this, which is that of the neural memory module update mechanism. Now, the Titan architecture uses a feed-forward neural network and tries to use its weights as a sort of neural memory. And every single time, it uses this network to predict some tokens that it appends at the beginning of every single time step when it's giving tokens into the transformer model. Now, in theory, this sounds like a great idea. And in practice, it's because of the previous results we've shown, it actually does work pretty well. There's a huge problem, though. They decide to update this memory based on the notion of surprise. If a sample or training example is more surprising, as in its gradient is much higher, they want that to affect the weights of the memory more than if it isn't as surprising. And they use a linear combination of present surprise and past surprise to do this, and as well as a forgetting mechanism just to ensure that over time, surprise gets decayed out. There's a small problem with this, which is that A, it's extremely simple, and you're simply using the gradient magnitude to weight how important a sample is, which may not always be the case. If you have a training data set and you have some samples that aren't really representative of the underlying distribution, then those samples might be really surprising, and the memory might then get adjusted massively to reflect that, even though it's not actually reflective of real-world task performance. This creates a massive problem and can lead to overfitting and worse real-world generalization, which is what we saw in our tests when we were just running the Titan model without the solution that we will then propose. Which then leads to a question. Can we design a different definition of surprise, which then completely changes how this memory is updated, and as a result makes it more stable, better in real-world task performance, and actually leads to better results? And the answer is yes, which is our main contribution, expected gradient divergence weighting. Effectively, we treat the parameters and the gradients as a random variable drawn from some underlying distribution, and we try to redefine the notion of surprise using a few mathematical inequalities based on how much these random variables differ from their expected value. And this actually has some pretty interesting implications. We're able to use two different notions of surprise. The first is local surprise, which is how surprising a given random gradient update is based on the gradient distribution. And the second is global surprise, which is how different a gradient update is with respect to all possible gradient updates given all possible parameters. So this actually has some interesting results. First of all, this obviously mirrors the Titan's contextual memory, which is the local surprise thing that they were doing, and the persistent memory updates. But second is that as a result of this mathematical justification, we're able to see much greater results. Now, I won't go too deep into this because this is very mathematically dense, but TLDR is that we use Markov's inequality and Jensen's inequality to basically weigh the surprise inversely to how likely it is to occur. So, for example, by Markov's inequality, if a given gradient has, let's say, 1 over k chance of occurring, then we weight it by the factor k. And similarly, by Jensen's inequality, there's some second-order mathematical correction terms we had to add, but we weigh it in accordance to how much it diverges from the parameter's total global gradient. And this has some very interesting results. First is that our update becomes slightly more complicated and has very slightly more computational complexity, and we have to maintain a running average of the gradient norms and a running average of the actual parameter norms themselves. And at each iteration, we just compute the norms of the gradients across all the different parameter groups and all the weights. And we simply divide the expected value by the current gradient, and we divide the gradient of the expected parameters by the current gradient as well, which gives us two values for our surprise. Then we simply multiply this together and use it to update our existing surprise metric. The good news is we don't really have to consider old surprise in this case because it's actually built into the running expected value amounts, so that's definitely a plus point. Now, we decided to evaluate this on the Fine Web EDU dataset, and we ran 31 runs for 19 epochs on the GPT-2 tokenizer. There's some statistics here if you'd like to go deeper, but the results are the most important. We ended up seeing massive performance gains across the different 31 trials, and it almost successfully beat every single Titan module across all the time steps, which indicates stronger real-world test generalization due to stabler expected value-based gradient updates. And while the loss was higher for the initial phases, any gains our architecture made was actually retained much further. And as a result, it was seen to have better generalization and real-world test performance. So yeah, in the future we have some things that we want to explore, but yeah, that's pretty much it.